All right, so in my notes, I said we're going to talk about ohm meters next. But you know what? I just looked through it real quick, and there's a bunch of stuff I crossed out. Said, it's being a little too much. It's kind of doing the same thing with the meter movement and stuff. It's like, don't need to do that. You got it. So I don't really need to write anything because you know all of this. I'm watching you guys. Ohm meter measures resistance. Takes readings with the power off. Unless you're talking about the meter, then the power for the meter has to be on, yes. Works on the same principle as a voltmeter because it's still a meter with a little movement in there, and you have to have movement across that little device. It uses internal batteries to provide that meter movement. Batteries inside tend to wear out over time, so you have to replace the batteries, and every time you turn it on, you have to zero it out. All right. Let's see. I kind of feel like, well, not feel like, I know for a fact. I talked about Wheatstone Bridge yesterday, and I thought afterwards, I really need to redo the whole way I teach that. And I don't want to go back and belabor the whole point, but one of the things that I knew for a fact that I could have done a little bit better is, of course, you know, Wheatstone Bridge I drew like this. And if we draw a little more simplistic one, why couldn't I just draw a box and then turn the whole page? This is a little simpler, a little sloppier, obviously. I got the battery right there. And we have all of these points on here. One of the things that I think is helpful, oops, and the meter goes right across here. Here's the meter. And I said when it's out of balance, then you're going to get movement between, we'll make this point C, D, we'll make this A, we'll make this B. So when the bridge is out of balance, you're going to get current flow through points C and D, which is going to cause your meter to react. Well, I think if I drew it just a little bit different, it might be more meaningful. Because this is all it is. Right? That's the same thing. You just put the points here. A, B, C, and D. And the meter goes right there. And if we thought about this a little bit more, just to kind of make sure it makes sense, if this was 10 ohms, and this was 20 ohms, and this was 10 ohms, and that was 20 ohms, if we were to do EIR across all of that, and hopefully you can just see it without doing it, if I put a voltmeter between here and here, what would that voltmeter read? Or do I have to do that? Let me see. We could do this. Let's say this is 12 volts, just because. What's my total resistance? 15? 15 ohms. So what is my total current flow? 0.8 amps. 0.8 amps. All right. So then what does that mean over here? Well, we can't just do one circuit, right? Because we're doing series parallel. We'd have to combine it. So just to combine it real quick. This is the 10 and the 20. So how many ohms do we have? 30. And this is 30. And so we have a parallel circuit. So it's 12 and 12. So the current flowing through each phone is going to be 0.4 and 0.4. Okay, well, since they're the same, that goes into here. So in series, this is going to be 0.4 amps and 0.4 amps. Yes? So this side has got 0.4 amps and this side has 0.4 amps. Hope everybody saw where I got that.
Can you start over from 15 amps?
15
Or
amps.
15 ohms?
Okay, so do you know where I got the 15?
Yes. So you got 20 plus 10
Okay.
because they're series. And then
So we have to combine. So we're going to, okay, let me go a little bit slower because this is a big good thing. So if I go a little bit slower, I have to,
two series.
let's get rid of this. It's a series parallel. So I have to redraw this series parallel. So I'm going to redraw it down here. So I have a battery. And the battery is going into but it's now we're just going to have two. So if this is R1, R2, R3, and R4, then this over here is going to be R1 and 2. This will be R3 and 4. Okay, we're going to combine them. So if we combine them, then the resistance of these two, because they're in series, is 30 ohms. And this would be 30 ohms because it's exactly the same. And I said this is 12 volts. And so 12 volts across any parallel circuit, how many volts are over here?
12.
And how many volts over here? 12. And so then we just did the math. Well, 30, 1 over x plus 31 over x. Answer 1 x minus 1. Or I just know that two resistors in parallel of the same, you just divide it by 2, so it's 15 ohms. But we know how to answer that. And then we did the math, and we say, well, that's 0.8 amps. So I know that 0.8 amps comes through here, and it's going to split evenly. Or I can do the math, E divided by R, and I'm going to get 0.4 amps. 0.4 amps. Well, 0.4 and 0.4 is 8. The 12 carries over, and we discussed that. So there we go. So now this is R3 and 4 is 12, 4, and 30. So I come back over here, and I know that 4 amps is going in series 3 and 4. Well, then that's got to be 0.4 and 0.4. Can't be anything but. And this is 0.4 and that's 0.4. Can't be anything but. Now I can just do Ohm's law on this right here and figure out what is my voltage drop across everything. So this would be
4 volts.
4 volts, and this would have to be
8 volts.
8 volts because 8 and 4 is 12, and this is the same side, so they're the same numbers, so it's 4 and 8 volts. Okay, so across R1, if I put a voltmeter across there, I'm going to drop 4 volts. And if I drop 4 volts here, wouldn't then points C and D on both sides be exactly the same? At that point. So at this point right here, the voltage is the same on both sides. No matter how I want to measure it, I'm going to get the same thing. So if I go across R3, I'm going to get 4 volts. If I go across R4 down here, I'm going to get 8 volts. So what would the voltmeter right here say? 0 volts. So that is a Wheatstone bridge in balance. Okay. Now, what we could do is just invert these. I guess since we know all the numbers really quick, that would make sense. If I inverted it, and this is one of the things, again, I hate about my little tablet here, is I just don't have enough room. So let's just say we invert this side right here. Follow? Rather than doing all this math over again, we're just going to flip it. So this time we've got 4 volts, 0.4 amps, and 10 ohms. And this is 8 volts, 0.4 amps, and 20 ohms. But this side, I would have 8 volts, 0.4 amps, and 20 ohms. See that? Down here, let's do this one. 4 volts, 0.4 amps, and 10 ohms. Well, now it's completely out of balance. So we've dropped 4 over here, we've dropped 8 over here, so 4 here and 4 there. So what's the difference between the two? So now we're going to get 4 volts flowing. So this is be 8 over here, 4, so we got 8 volts. So it's out of balance. Well, if we go back to this original drawing, then what we would say is this one right here, that's my variable resistor. That's the zero out knob. And this one right here, that is the unknown. This is actually your red lead and black lead. So red lead and the black lead. That's what you're measuring.
And so when we invert it, we create a.
Well, I just inverted it to explain that when you have an imbalance,
Right.
you get something.
Which is a 12.
So what does your meter look like when you put it in balance? Well, you take these 2 leads and you connect them together, right? Your red and your black. And then you rotate this one until you get 0, right? Then you put a resistor in here and you get an out of balance Wheatstone bridge circuit, which is going to cause voltage to flow because you have internal batteries, going to cause voltage to flow through it to give you an indication. That's what you're doing. And because you have different ranges are going to have different resistor values, and those resistor values might need more voltage or less voltage. That's why you have inside, you have D-cell batteries and 9-volt batteries. Because some of them need more, some of them need less.
And each setting, there's like a different resistor.
Different set of resistors and stuff in there. So hopefully that made more sense on a Wheatstone bridge and how it worked than what I left you with yesterday. Are we happy with that?
So does that mean each setting has its own Wheatstone?
Let's just say yes. I don't know.
Okay.
I don't really know.
No worries.
I did not design one. All right. Okay, we got to learn all about that. Let me see. All right, let's move on to something completely different. Probably much easier. We'll see. Oh yeah, before we do that, let me just make sure. Always zero out the meter, use the center 2/3 of the scale. Don't use an ohm meter with power on the circuit. Digital ohm meters. How do you zero them out?
Short it and then subtract, add whatever the value is to the.
You got to short them out and read the meter. So for some of you who are now working on the battery project, where you're working with like a 0.1 ohm resistor, this will measure the resistance. If you stick it across there, you're going to be wrong. So you got to take the leads, short them out, read the meter. Meter says 0.5. And you go to measure. Who's doing it? Somebody I was doing with has a 0.5. Yeah, we did a 0.5. So
Well, because Kelly gave me a 0.5.
yeah, but what did the meter say? It said 1.
Oh.
But we know that wasn't right because when we zeroed out the meter, it said 0.5. Then you measure the resistor and it said 1, but we knew it was printed right on there, 0.5. Follow? So,
You add or subtract.
okay, so if the meter,
I know you touch it together, and whatever you get, you add or you subtract that from the.
well, let's just, that's a really good question. Let's think that through. So if you touch the leads together and it says 0.5, so how much resistance do you have built into the leads going to the meter? 0.5 ohms. And so now you measure a resistor and it says what's it, 1.0. Well, we had 0.5. Should we add that to this?
Subtract it.
You sure? You want to add it? So 1.5 now? Remember, this said 0.5 on it.
Oh,
So we're going to, now the meter says 1.0, so we need to
subtract.
subtract because we have 0.5 already showing on the meter.
Right.
It's reading 0.5 too much. So we subtract it, so we get 0.5. So that's what we get, and that matched the resistor. And now it looked like some John Madden play just happened on here. Remember that guy. All right. And Mega Ohmmeter. What's a Mega Ohmmeter? Or Mega Ohmmeter? measure very high resistances, high values of resistance, mega ohms. So if you see it on the test, mega ohms, well, I don't know what that is. All right, let's talk about symbols and wires and all that good stuff. So symbols, not the kind that you beat together in the band, but this type. Symbols. I really sometimes hate this program. Have I said that yet? All right, symbols. Start with some easy ones. A conductor. Also known as a wire. This is the easiest symbol of all. It looks something like that. All right, but when you're working with your diagrams, let's see, this is the older convention. Older convention. If you have them like that, that means they're connected. That's a connection point right there. And the not connected would look something like this. So not connected. In the newer convention, the connected would look something like this, with a little dot right there. And the not connected looks like this. Well, can you see the problem?
Yeah.
So I don't care which way you do it. What I'm going to look for is you're going to look for something like this with a little loop, or I'm going to look for the dot, and then I'll know which way we're going. So,
Don't mix them up though.
but yeah, don't mix them up. Well, I use a little bit of new and a little bit of old. Well, I guess if you mix them up, and you mix them up with the connected as a dot and the not connected as a loop, you're fine. It's where you mix the connected up here and the not connected that you get into trouble. Right, okay. Shielded wires. All right, you've already got to experience the shielded wire. And shielded wires, kind of the one I like is this one. Sometimes you can just see it like this. So shielded wires, as do I have pictures of them? No, I don't. As you experienced, our wires in aviation are Teflon coated. They're pretty tough wires. The nice thing is they are Teflon coated, so they pull really nice through bundles. They're very slippery. But man, that shielding is really tough stuff on there. But you've seen in the project we had to check continuity that most of you did it correctly. It was a really good class. It has that wire braiding on top of it. So that's a shielded wire. Now that shielding isn't really abrasion protection. It is radio noise protection. Like for example, all little planes, almost all little planes, that have magnetos. We have a magneto that generates 18,000 volts for the spark plugs. It takes one wire from the magneto, one little wire runs from the magneto inside the cabin to a switch. And when that wire is grounded, the magneto is off. When you unground it, take the ground off, the magneto is on. And now you have this wire that runs all the way into the cabin, about next to the radios, that has a lot of voltage pulsing through it because it's got nowhere to go. And so that would create radio noise. So what you do is with the wire, you got the wire, on top of the wire, they put all that metal braiding on top of it, right? And that metal braiding is then broken off at the very end and sent to ground. So what happens is these pulses, this radio noise, because you have all of this voltage going through a wire. Whenever you have voltage going through a wire, You have magnetic fields expanding and collapsing, and especially this particular item because it's constantly pulsing, so it's going to build up, collapse, build up, collapse. That creates voltage, that creates radio noise. It's going to, if you will, get trapped inside of that steel braiding, and then it sends it to a ground. So you don't have this radio noise problem. So that's what the shielding is for. Now, the funny thing, I don't have the exact answer for this. I've seen it sometimes where they want it grounded at one end and opened at the other, and I've seen it other times where they ground it on both ends. But I think more often than not, it's grounded on one end and not the other, which is kind of bizarre. But
I think
the shielding is grounded,
right.
and then the wire on the inside does its own business.
Is that just for the magneto or for other applications?
You do it for other applications, like my airplane. That's the only place you'll find it. Now, one of the things, of course, that I had you make sure is that this shielding was not touching the center conductor of the wire. Well, if the shielding is touching the center conductor of the wire, then really what you've done is you've taken a wire and you've stripped, you've got power on the inside and power on the outside. Is that the kind of wire you'd want to grab onto? No, okay. And so if it's on an airframe, what this metal shielding does is it touches metal around the airplane because it's supposed to be grounded. It's supposed to go to the ground of the aircraft. Well, if you got power running through it, then you have a short. And that means you're going to have a smoke and a fire and heat until it pops the brain. Fire in an airplane is a really, really bad thing. That is something that every single pilot is just terrified. I know, I'm terrified of it. Yeah, I don't know. Now, I don't have air conditioning in my airplane, so I do fly in shorts, but I know a lot of pilots won't fly in shorts. I don't fly commercial in shorts. I always fly commercial with cotton pants, no polyester stuff, cotton shirt, usually a long sleeve cotton shirt. Just fire. I don't know. Freaks me out.
I think one of the reasons you generally don't want to ground both ends of it is that if you have a significant resistance or potential between the two ends of the wire, like the engine and the rest of the airframe.
Oh, that's a good point. Yeah, you have a difference of potential between these. And he's right. So let's just say we have a firewall here. Well, that's such a good example. There's your firewall, and inside here is where you have your switch. And this is grounded to the engine. So this attaches right to the engine, and this attaches right on the inside. Well, the engine could have it's supposed to be grounded to the airframe, but sometimes it doesn't work all that well. You don't want this to be, number one, to be your engine ground. That's bad because it's going to pull out that little wire. And yeah, if you have a difference of potential for some reason, then you're going to have current flow through there. So that's not good either. I like that. All right, shielded wires. That's what you need to know about them. Yeah.
What's the correlation between wearing shorts and fires?
Well, if you're in a fire, this goes back to my Navy days because on Navy and the shipboard, I mean, when you responded to a fire, you just wore your cotton clothes. I mean, that's what they gave you back in my day. I don't know what they wear now, turnouts, I think, because I want you to die, but there are a lot of us back then. And so you would always, long sleeve shirt, roll it down. You'd take your cotton pants, roll it into your pants. Cotton doesn't burn as well. I mean, it'll catch fire, but if you're just wearing shorts and you got your legs exposed and there's a fire coming through the firewall, you're going to get burned really bad. So it's buying you some time. So that's why I don't want polyester will melt to you. Cotton won't.
Yeah, and then we have plastic shoes.
Yeah, then we wear plastic shoes. So, although I watched it, off subject, I watched a video the other day about the reasons why you might want to wear a helmet in the aircraft. Well, it doesn't work. That was A, that was B. This is also B, so whatever. Well, we've already covered resistors. Resistors. We all know that. I could almost skip right over that. Switches.
If you have a European aircraft, the symbol for the resistors get different.
What are their? What's their
They use like a little box.
little box?
Yeah.
There's too many little boxes though.
Yeah.
So I hate that. So all right, resistors. This is a picture of a rheostat. This is a pretty common thing to see in an airplane, where it's got a little wiper blade that goes across. This is a big resistor in there, so you can add or subtract resistance. the problem I have with resistors and rheostats and potentiometers and variable resistors is not every single book agrees with every single book. So I've kind of let it just kind of go. You guys did really, really well, though, in finding most of the time the exact difference between them. Because some of them have 2 posts and some of them have 3. Some are connected in 3, some are connected in 2. And so that's what you want to look for when you're actually looking at the schematic, whatever you're going to call it, how it actually works. So here, this diagram of a rheostat, you can see it's a 3-point rheostat, 1, 2, 3, and that's why I like this one, because that's really what you're doing. You can see there's 3 posts, 1, 2, 3. And so your wire is connected in 3 places. And this would be used for like a light dimmer. So when you want the light to be brighter, you're going to go this way. So I think about it that way. So if I went like this, and this was a light, would the light get brighter? It would, because I bypassed all of the resistance. And if I just connected it from here to here, the light would be dimmer because I've added and allowed all of that resistance. Then I pull it all the way back to the left, and it's going to go dim, 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 right? And of course, this one here just is implying that you have a resistor in series that you can change the value, like you would with the Wheatstone bridge or Ohm meter or something like that. So rheostat 2 terminals, potentiometer 3 terminals. And you guys, like I said, in this class, you guys picked up on that probably better than any class I've ever seen.
What's the bottom one labeled a rheostat?
What I started with
Yeah.
is the books don't always agree.
Right, yeah, okay.
And so for years I've just kind of been, geez, do I even cover this? It's like, how do you cover something when nothing agrees? But then finally I'm like, you know what? This is it. This is where I'm going. This agrees with more books than the other one. Let me see what other thing I wanted to write. I guess there's some other stuff I could write. All right. Nah, that was good. All right, circuit protection. We have fuses. Oh, this has got to be in here somewhere. Yes, I do have it in there, so I'll just get to that. Fuses. What is a fuse?
Non-resettable breaker.
Non-resettable breaker. I like that. They are placed in series. They are expendable. What does that mean? You throw them away. Throw them away by, I'm not cheaper, some are expensive. Man, trying to find fuses for some of the legacy airplanes. Like I had to find some fuses for my Cessna. They were almost impossible to find and incredibly expensive. Capacity is rated in amps. Now, if you haven't noticed, in my office, on my bookcase right there, I've got a chart of alternate fuses. Yeah, tin foil, nails, bolts, bullets.
Spanners,
What? Yeah, what?
spanners.
Spanners, yeah, wrenches, you know. They all come in different amps. My wife and I were kids. We were married, but we were married as kids. We rented this house. It had a shake roof too, and we went all out for Christmas, man. Somebody gave us all these Christmas lights, and how many, LEDs you can put like 100 of them, but back in the day you can only put like 4 in a row. It'd blow out the fuses. Not if you cut nails and stick them in there. Freaking idiots. Okay. We have current limiters. Oh, a fuse. What does a fuse look like? Like this. There's a symbol for a fuse. there's got to be current limiters out there. I know I've seen them. I don't like them. They're really more of a, well, here's what I wrote. Current limiters, such as used in armature circuit of a high current DC generator, is a form of a slow blow fuse, means the fuse blows very slowly, that will accept a surge of current greater than the generator rating. But if there is a continual flow of current in excess of the generator rating, it will open the armature circuit and remove the generator from the system. Current limiters normally cannot be replaced in flight. I've seen them as kind of fat wires that blow, and so you have to replace that little section of wire. So it's like a fuse, but it's not a fuse. It just looks like a piece of wire. And you're like, what's that piece of wire for? Why is it funny looking? Those are usually current limiters. Burn. Pop.
Same as a fusible link.
Fusible link, that's what I call them, yeah. This is a good one. So circuit breakers. Circuit breakers. So FAR 23.1357. Now the funny thing about FAR 23, since I've written a lot of my notes, they've revamped a lot of 23 stuff in there. And sometimes this stuff is no longer in there because they've gone to more of a whatever is approved as the aircraft is approved kind of a thing. So it's like, hate to say it, but it's more of a makes sense thing. So it's like if an aircraft manufacturer, instead of following all these very exact rules, they said, okay, you make an airplane, you show us that your airplane design and what you've done is safe, and if we approve it, you're good to go. As before, they would have all of these rules that we can't have that, you can't have that, you must have this, you must have that clearance. And one of the rules they had is that circuit breakers. And the sad part about these rules going away is you don't know them. And if you knew them, then you would know, okay, these are things that aren't aircrafty. So circuit breakers cannot be, we'll say cannot be automatically reset. So in other words, there are some circuit breakers that will pop, but they'll cool down and reset. So if too much current flows through it, pops, it cools down, it resets. You don't want that in an airplane. As a pilot in command, if I want to pull a breaker, if a breaker pops, I want that out. I'm done with that. I don't want you, especially if it's, if I'm on a day VFR flight and I've got my landing lights on just because it's safer to have them on, and that circuit breaker pops, well, something happened. Something got hot in there. And that wire was maybe starting to melt, catch on fire. I don't want it to continue, So the insulation, it's hot, the insulation maybe started to burn off, and now I got a bare piece of wire in there, and, the circuit breaker was slow to pop, but it did. Okay, but now that piece of bare wire is landing, and it's sitting on top of something metal, and it resets, and it starts going again. I don't want to pull it. I want it off. You stay off. So... but that's not to say that the pilot can't override it and push it back in. Absolutely, you want that choice. But it can't reset all by itself. So resetting must be manual. What kind of circuit breakers do we have? Well, they need to be in series, which hopefully that makes sense to you. If you put it in parallel with something, well, that didn't work. It just goes around it. They should be resettable. There are three types of operation. We have the push to reset. I hate this type. I think my Cessna has a bunch of them. You can't pop them. They're flush mounted. It's just a button, and you can't grab your fingers on there and pull it out. It's very flush. When it pops, it'll pop out, and you can push it back in, but you can't pull it out on your own. Not a fan.
There's a reason for that design?
No. I don't know. Pain in the ass. It's somebody's dumb idea. There's the push-pull, which is exactly what I replace my circuit breakers with when I replace them. I can pop it out, I can push it in. I control that. If I don't want that on, I pop it out. I like those. And I have a couple of these in my airplane now. The toggle type. It looks exactly like a toggle switch. Single pole, single throw, double pole, double throw, looks exactly like it. The only thing about it is when you look at it, right at the very end, it has a number in there. And that's how many amps it is. So there we go. Nope.
When those activate, does it actually move the switch or just disconnects the circuit?
It's a switch disconnect. Like you can use them as breaker switches.
But does the lever actually move?
Does it push it?
when
Oh, what's inside and how does it work? I don't honestly know. If I told you, I'd be lying. I've never taken one apart. They're expensive.
You never had a retail one. I'm just curious
Like a
whether
circuit breaker
it physically moves the lever
pops
when
and
it
resets.
breaks, or does it just do it internally? You have to.
Oh, so like if you have it on, does it go click down?
Right.
No, I don't think it does. It just pops inside. There's like, I believe it's bimetallic strips that pop out from the heat, and you'd have to reset it down and up.
So it's no different than this circuit breaker in your house.
Yeah, which goes halfway.
Right.
Yeah.
Yeah.
How do you know that it's pumped?
Maybe it does go halfway. I don't know.
Something turns off.
Yeah, 'cause I was going to say, my radio quits. I go, well, let's retry that. So I think I have one in my airplane, and it's a weird thing. The guys who wired my radio said, you're going to love us for this. It's called a ground comm switch. And so normally like in an airplane, you power it up with a master switch, and then that will start your basic electric stuff. You know, your gyros will start turning, your lights are on and stuff like that, but your radios are still dark. And so then you have a master for a radio master, so you'll click on the radio master. But in my plane, I have one switch, it's called ground comm. So if I just click that, the entire aircraft is dark except for my comm radio will pop up. So, and the point behind that is if I want to talk to ground, I don't have to power up the whole aircraft, power up the radio. I can just pop on the radio. Or in the event of some sort of catastrophic electrical failure where I have to shut down the whole aircraft, I can pop that on and still talk to a controller and say, hey, I've lost everything but this. And so, they've said a lot of pilots have called them up and said, man, that was like the greatest thing ever. They've had problems. The other nice thing about it is, as long as the aircraft battery ground is still connected, if that's not the one, it's a whole independent wire coming off the battery. So it really is isolated. That's off the top. Okay, so let's see, resettable, push. There are,
Is there a symbol for a circuit breaker?
yeah. So the symbol for circuit breaker, I didn't do that yet. Now, I do this one, that's the push-pull type. And I want to say, what's the one for not push-pull? I think it just has that. Yeah, just has a little mountain with the little flag on it.
Are there rules as to what kind of circuit breakers you can use for different systems?
Not that I'm aware of.
No, it's just whatever you.
Whatever's appropriate. All right, I got 3 different types. Because I already just said there's 3 types. Now I got 3 types. So, wow, D-I-F-F-E-R-E-N, different types. We have the magnetic type. Of circuit breaker. When excessive current flows in the circuit, it makes an electromagnetic strong enough to move a small armature which trips the breaker. So without writing all of that, it uses magnetic strength to open. So obviously it's set for a certain amperage. That's how circuit breakers are rated, for amperage, just like fuses. So you're always going to look, there's always a number on it. 1, 2, 5, 20, 30, 0.5. That's your amperage, how many amps. And so knowing how many amps are allowed to flow through it, and we know that current flowing through any sort of coil is going to make a electromagnet. So we could set this up to the point where we can say, okay, if this electromagnet has the equivalent of 2 amps, then it should pop open. There's the thermal overload. Uses a bimetallic strip. So as the name implies, bimetallic means it's made out of 2 different metals. These 2 different metals are fused together, and when they, in fact, I got some cool bimetallic toys at home I should bring in. When the heat goes through it, they're going to expand at a different rate, and so they'll bend. And when they bend, that's the tripping action because they got hot. So use bimetallic strip, which bends when overheated or when heated, and trips.
Does that share some similarities with like a thermocouple and 2 similar metals, and heat's introduced and you get like this small voltage, but just in this case the 2 metals just...
Yeah, it's the same theory, but they bend instead of making a... Yeah. I wrote this one here. I don't know what I'm talking about. So the trip-free circuit breaker, CB circuit breaker, will allow the circuit to be broken. Will allow circuit to be broken even if pilot holds the button in. So in other words, the circuit breaker has tripped and it popped out, and the pilot says, "Oh no, you don't. That's the coffee maker and I want it on." And so the pilot overrides it and holds it in. It ain't gonna work. So it's called trip free, and so it's not gonna reset inside. It's smarter than the pilot, thankfully. All right, big point here. Circuit breakers are designed to protect the wire. Yeah, you got to remember that. Write it down. Remember it. Circuit breaker protects the wire, not the component. Not the component. Therefore, the circuit breaker, CB, save time, must trip below the capacity of the wire. So, all right, so you're playing around in lab over there, and you've got an 8 amp little motor. That's what that thing is, if I remember correctly. Is it 8 amps? 8 amps? It's rated at 8 amps. So you're using what size circuit breakers on that? 5 and a 2. Which one's going directly to the motor? The 5. Does that make sense? Wait a minute, it's an 8 amp motor. Why don't we have an 8 amp circuit breaker?
That's what I was thinking.
Huh?
That's what I was thinking.
Because we don't care about the component. We are selecting the circuit breaker based on the size of the wire. Circuit breaker protects the what?
The wire.
The wire. You care about the component?
And in protecting the wire, it protects the component.
Don't care about the component. Component's fine. It's going to be fine. What we really, really care about, and you're right, it does both, because we're worried about that wire running from here to there catching fire.
Okay.
That's a big, big deal. I suppose chances are that component having a failure and causing a short that's going to cause a fire isn't, this is my opinion, isn't as likely as that wire that's running all over the place, working its way through a little tiny piece of aluminum and touching the aluminum and shorting out. And then when that shorts out, everything from that point all the way to the bus bar is going to catch fire.
So like when drawing a schematic, you have the battery and then the wire. You have the circuit breaker before the component.
The circuit, no, because if you run the wire 100 feet and stops right here, and here's the component, and I put a circuit breaker right there, did I protect the wire?
Wait, say that again?
If you put the circuit breaker at the component,
Before the component.
right before the component.
Uh-huh.
So in other words,
So I'm thinking like the flow of the.
I got a battery, and I have this wire, and this wire runs 100 feet, and it finally gets to the motor. Right, there's a motor. You're like, oh, wait a minute, I forgot to put a circuit breaker. Okay, so we'll put a circuit breaker, we'll put it right here. So now, we'll put a circuit breaker right here, circuit breaker on the motor, there it is, back in the tail.
So you're saying don't do that because 100 feet is still good.
That's going to burn.
Right.
So you get a short right here. It wears through and starts rubbing on the piece of metal.
It's right under your seat.
It's right under your seat.
So we want to put it. Close
So what happens? Oh, this circuit breaker, I suppose, could pop. Probably not, because all of the current goes from here to here directly to ground. And so this doesn't know anything. It's like, we're fine. Don't worry about a thing. Meanwhile, this starts smoking and catching fire. And when does the fire go out? When everything is done burning, because it is connected to the battery.
Is there like a recommended distance from the load, from the battery to like how far you put a circuit breaker?
Yeah, that far. You put the circuit breaker at the source. At the source.
They were screwed directly to the bus bar.
Yeah, it's screwed directly to the bus bar. There is no wire.
You did say that yesterday.
You literally have the bus bar, and the circuit breaker is screwed to it like that. And then there's the component. And then then there's a small wire, then the switch. So everyone is just screwed right to it. So where's the wire? There is no wire. So now, in all fairness, if you go look at my airplane, there is not a gigantic circuit breaker on the battery. There is a solenoid that you can disconnect with a switch, kill the battery should I need to. You don't fuse it back there. All right. I already said this, aircraft do not use automatically resettable circuit breakers because they must be manually reset. That brings me to switches and 920.